Hello, assalamu alaikum, and welcome today in our new episode entitled Trust Your Model Through Explainable AI. So, we will explore how to gain deeper insight into machine learning models using a various methods from the field of explainable AI. And we will cover topics such as understanding what our model is learning and identifying which parts of the input are most crucial for our predictions. And of course, how to ensure the robustness of our model. Okay, so to start, an AI system and machine learning are now used in many areas. So, of course, are used to develop to solve or to develop, or let's say solve better, to solve some problems and help people, of course. So this success is largely due to the improvement of deep learning and the new ways of using data. So as we're noticing, every half second we're having a new technology, we're having a new model in the market. So it's really we're having a very large and a fast improvement in this area. However, the systems have become more complex, or let's say very, very complex, but even experts can't fully understand how they work. And that's why they are often called some black boxes. So, like everyone who start ever doing machine learning, we always pass by some parts where we say this part is, let's say, it's hidden, it's a black box. We can't really see what the model is doing there. Especially, we're talking a lot about that in neural networks, about weights and those randomness and so on. So we all heard about the black box in machine learning before. So at the same time, machine learning is used in important area like healthcare or self-driving cars, where it's crucial to understand what's happening inside the system. So we should understand to see if the system is doing the job correctly or not. So we can take the risk and build a system for healthcare, for example, and we just like say, yes, it's a black box, and yes, you will get great output by the end because we test it. No, we don't work like that. We just like need to understand exactly what our model is doing to just like to confirm that yes, is doing it right. And this is where the explainable AI comes in. So it's helped us to make a stance on how those algorithms works. Okay, so let's say majority of time we used to build models, especially when we're talking about those new technologies, or let's say starting from neural networks. So some code, generally they are hidden. We don't really understand what's happening inside, how the model is working, how we're getting great answers. But with the explainable AI, so finally the user here can understand why not it can do that, why it failed, why I should trust the model, and so on. Fine. So what is this explainable AI? So when building models from data, there is often a trade-off. Let's say we can choose simple linear models that are easy for human to understand, but they may not provide the best predictions for more complex problems. In the other hand, or we can use a highly nonlinear models that perform better on a wide range of tasks, but they are too complex for human to easily interpret and understand. For example, the neural network often have millions of parameters, which are far beyond what a human can understand and can comprehend. Okay, so sometimes we have a lot of neurons, a lot of relationships, a lot of, let's say, very complex architecture of a neural network. So here, even if, let's say, if you are advanced in the field, you may not understand how the things happen. So explainable AI here help in this area. So explainable AI here refer to the collection of procedure and techniques that enable the machine learning algorithm to produce an output and a result that are understandable, okay, and reliable to the human and the users in general. So when we check the output of the let's say the output of the explainable AI, so not a simple human, but at least a machine learning developer can understand what's happening inside this model and how this model is doing this predictions. Okay, how that it's clear. So sorry, we generally have two options to understand how my model is doing X, Y, and Z, how my model is doing the task. So either we make sure that the machine learning model itself is understandable, interpretable. Let's say a normal human can understand it. Let's say we have some sort of models that are easily, and so a normal developer can understand how this model is performing or what it's doing. Okay, comparing to other complex model. So in research, let's say this approach are called model-based and post-hoc. So post-hoc methods can be further divided into black boxes and white boxes approach. Okay, so the black boxes approaches are used when we don't know much about the model. Okay, so it's a black box. And we only look at the relationship between the input and the output to explain its behavior. Okay. On the other hand, we have the white box approaches are used when we have access to the models and internal data, internal information, such as the gradients or the weights in our network. So whenever you can access the weights, or you can understand what's every step or everything that is happening inside your box. So it's white, it's transparent, it's clear for everyone to understand it. Okay. So the field of explainable AI also involves studies, let's say, the what's make good explanation and which type of work best for humans. So while we don't dive into let's say in deeper in this topic, but we will focus on the various algorithms and methods available for explaining the machine learning model. Okay, so here, as you can see here in this graph that we do have, we have some models here where we can understand it. So the model itself is understandable, so we can understand the data. And we have neural networks, for example. We don't really understand how the model is performing and what we are exactly doing inside this model. Good. So, of course, explainable AI, let's say, have some multiple algorithm or libraries that may help us to do those specific things. And one of the most famous methods that you can use is SHAP. So SHAP is a popular explainable AI technique. So it's a method used to understand the contribution of different features that was included or was a part of the model's predictions. Okay, so it draws the inspiration from the cooperative games theory that we will talk about it in the next slides. Let's say specifically the value of the Shapley values. Okay, so this is one method that's helped us to understand the contributions of features. Okay, so and as I mentioned, it's just, let's say, it's inspired from the theory of Shapley values. So what is this theory, or this game, let's say, this game theory? So just, let's say, imagine a team working together in a game, and each team member is contributing differently to the team success. Here we're having the example of Kaggle competition, let's say. So here, imagine you form a team, and then to solve one Kaggle challenge. Well, and yes, by the end of the competition, of course, you will get you will get a prize. Okay. So here, each member contribute differently to the team's success. Okay, they don't always have the same level. So after winning the prize, the question arises if how to fairly distribute the winnings. Let's say if the prize here, I don't know, maybe 10 millions, or let's go with 4 millions to it. So here, the normal way that we do, each one will take $1 million. But in fact, no, they didn't contribute the same way or with the same manner. Okay, so here, if you want to fairly distribute this price, we use what you call it Shapley values. And this Shapley values was introduced by Shapley, of course, in 1951, that provides a solution to this problem. Okay, to distribute for the fair distributions. Okay, so Shapley values here determine the average contribution of each player or each member here in the team to the payout. So ensuring a fair distribution. To do this, the method compares the team's performance with and without a specific player. So considering all the possible subsets of a player's account. For example, let's say if I remove person X, will we still taking the first place? Maybe no, maybe we'll be the second or the third place. So if the first place is for 10 million and the second place is for 7 million, so I mean the team, if there is no this person X, the team will take 7 millions. I mean 3 millions was right thanks to this guy here plus its contributions. Okay, so we just like try to create some subsets of those players and to check how good this team will do, to finally know how much each player or each team member here contributed in taking this place. Okay, so it just like try to consider the interaction and how they helped gaining this place. I don't know if it was clearly explained or not. So do you have any question, guys? Any question? Is it clear about the theory here? I don't know if I explain it better, but just like imagine it. I don't know if you thought about it before and while participating in hackathons or in challenges where one team member do the majority of the job, the other one do some simple design or prepare slides for the pitch, and then when you take the prize, it will be divided by all the team members. So here the Shapley values or the shape here theory of game here change this. Let's say how fair to distribute the output there. Okay, so apparently we don't have any questions, so let's move on. Okay, so that was for real life, participating in real life. Now let's leverage this to machine learning, how we can apply this Shapley values to machine learning. So using what we call it SHAP. Okay, so SHAP here leverage this concept to explain the individual predictions of the black box models. So instead of players, it treats each feature. So here in the model, we have data. This data contain features. So features in the Shapley values, they represent the players that we have. Okay, so we don't have players in machine learning models, of course, but we do have features of the data. Okay, and the model predictions here became the price that the team will take. Okay, so the prediction is the price, and features are the players. Okay, so by calculating Shapley values here, Shapley values, SHAP here determines how much each feature is contributing to the predictions. For example, in a stock prediction model, it can reveal how factors like age or gender may influence the outcome. Let's say, if you we'll see in a minute the Californian data set. In the Californian data set, we have we want to predict houses. So we have the latitude, the number of rooms, the price of I don't know some houses and so on. So here, if I apply on it this SHAP methodology, so it's helped me each feature. How important is it? For example, if I'm trying to predict houses and they collect a group of data of house prices of houses, so here maybe I can add in my data the name of the owner of the house, the age of the owner, and of course I add the surface of this house, how many rooms, how many bathrooms, how many other things. So yes, some attributes, some features may help detecting the price, but others no. For example, it's really clear that the name of the owner of the house will not really help me in the prediction. So here I'm expecting that shop value here will tell me that yes, this features is useless, you can remove it. Okay, so I hope it's clear. If it's not clear, please don't hesitate to ask. So here I have a collab of the California dataset. So the California dataset here, it's a famous dataset of housing prices, detecting housing prices. Okay. So it's contained a couple of features such as the location of the house, the size of the house, the average number of rooms, how old is this house when it was created, longitude, latitude, and so on. Okay, so we have a couple of information about the California in this, a couple of features in this California dataset. Okay, and we predicted features, but we don't know how good the model is doing. Okay, is it really good, or we just like the predictions that we did while testing was correct, but we really don't know which features are helping this. So to solve this problem, we're using XGBoost, and of course SHAP. Okay, so we're calling the SHAP method as well. So we're calling the data, we feed the model our data, and so on, and then we go directly to the SHAP explainer here. So here the SHAP explainer creates an explainer object that will be used to explain the model predictions. Okay, because the model here will predict. I will give it some information saying that the location of this house is, the size of this house is, and then the model will predict price. Okay. Based on what this model predicts this price. So I need an explanation. So for this explanation, we can use this SHAP.explainer to our model. So here, how does this work? It's create an object. Okay, as you can see here, it creates an object that will be used to explain the predictions later. Okay, and we have the explainer method that calculates the SHAP values for each feature in the dataset. And these values here represent how much each feature contribute to the model predictions. Okay, so here, starting with the first one, waterfall here just generates some waterfall plots, okay, for the first predictions. So here, this plot here shows how each feature value contribute to the model final prediction. So it's a start with the average prediction and then sequentially add the other features. Okay, so as we can see here, if we want to explain here, so here those are the features contributing to push the model output from the base value, which is the average model output over the training data set, and the model output here. So features here pushing the prediction higher are shown in red. Okay, so the features that have the model that push the prediction to higher, they are in red. Okay, and those pushing the prediction lower are in blue. Okay, so here we can see which features are doing what. Okay, so red here, they are pushing higher. Blue, they are pushing lower. Okay, so like that, I may understand maybe this latitude is not is in red, so it's pushing lower. Same thing for the populations and so on. Okay, we have also many other contributions or many other things. So, for example, here to understand how single feature. We're using this scatter here with the latitude to understand how single feature affect the output of the model. Okay, so we can plot the shape of that specific value. For example, here latitude, or you can use any other feature versus the value features of all the examples, okay, in the data set. So here, since shape value here represents features responsibility for each change in the model output, so the plot below here represents the changes, the change in predicted house price as the this feature here starts changing. Okay, so when this feature change, the prediction will change. Okay, so here we have this vertical dispersion at a single value of latitude represent the interaction effect of the other features. Okay, we have also some other representations. For example, here we have in this representation here is just like to get an overview of which feature are most important for the model. So we can plot the shape here values for every feature for the for every sample here, and the plot below shown here in this graph here, the plot here. Let's say sort the features, but the sum of shape value over all samples. Okay, they are here. We're using here shape values to show the distribution of the impact of each feature has the model output, and the color represent the feature. So we have here red is a high and blue is low. This reveal, for example, the higher median incomes to improve the predictions of house prices. Okay, so of course there are plenty of other example of other representations. We can also use that on images to show which pixels inside the image is helping getting specific predictions. Okay, so that's it. Do you have any question, guys? Okay, so I think the code wasn't really clear. So for those who will watch the record later, so you can find this here. I also can share, I don't know if I have the link. Okay, you can see the official documentation of SHAP in GitHub. So you can find plenty of examples. So this is for, let me, okay. So yes, for those who want to explore other things, just like try to check the library GitHub repository. Well, they really explained every single thing. Fine. Do you have any question, guys? Was it clear? Yes. Do you have question? And of course, SHAP is not the only one method that we do have. We also have LIM as well. We have some like about 3 or 4 other functions, and let's say every method is used for specific tasks. For example, here SHAP is focused more on some individual features. Maybe another method can focus on the globality or the general things about the general features or the general output and so on. So yes, that's it for today. We can wait a couple of minutes. If you do have question, do not hesitate to ask. Otherwise, thank you so much for those who attended the session, and see you in another episode, inshallah. Salam.